Action.
Honors Physics, F equals MA, review. You ready? What if you had a box? That's all you've got. It's got a mass of 5 kilograms and you're going to pull on it with a force of 20 newtons. What would you do to figure out what the acceleration would be? What are you going to write down? F equals MA. The only force is the 20 newtons. What are you going to put in for your mass? 5 kilograms. I don't know why I'm writing so sloppy. And the acceleration would therefore be?
4 meters per second.
Thank you for the units, 4 meters per second squared. Everybody got that? Now, this is what we discovered in lab last week, and we're going to build on it. What would happen if you took this box and you had another force going backwards of, say, 10, no, I'm going to change that. I'll make it 12 newtons. How would that change our work over here? You have 12 newtons going backwards. You'd have to change that 20, wouldn't you? To what?
20 minus 12.
20 newtons minus 12 newtons. The mass didn't change, right? And so what do you have now for an acceleration? And you guys are going to have to help me out. We're on video. 1.6? So really, this means sum, right? The sum of your forces. So forces forwards minus forces backwards is the net force. That's what we're saying. You got it? You good? Okay, let's try another problem. What if I had 3 kilograms and 12 kilograms, and I was going to drag it with a force of, say, 60 newtons? What's the acceleration? What are you going to want to write? Yeah, let's go with F equals MA. What are you going to write for F? 60. That's the only force. But now what are you going to put down for the mass? 15 kilograms, because that's the mass of the system. The whole thing is being accelerated by that 60. And the acceleration is now going to be what? 4 meters per second squared. Everybody got that? You good? Okay. Now you know what's going to come next. Isn't there a rope in there? I'm going to ask you to find the tension in the rope. Isn't tension just simply a force? Yes? Is there a tension pulling this box forward? But isn't the tension also holding that box back? So those are 2 tensions going in opposite directions. Why don't they show up in this formula? They cancel out. They're going in opposite. You can't grab somebody by the shirt and fly down the hallway together. Those are internal forces. What's the word? Internal. We need to take an internal force and make it external by isolating one of the bodies. So we're now going to just go with the 3 kilograms. Does this sound familiar? And now you have your tension. That's the only thing pulling this thing forward. So we're going to write F equals MA again. What goes in for the force? T. What goes in for M? And then what goes in for A? Oh, it's the same thing because we already figured out the acceleration. That's 4 meters per second squared. And what's the tension? 12 what? Newtons. Hey, is Newton a fundamental unit? No, it's a derived unit. It's a kilogram meter per second squared. Okay. Now, can we also try this with the 12? Okay, can I do it right over here? Okay. So what if I come over here and I write 12 kilograms? What's pulling the 12 kilograms forward? 60 newtons. What's holding it backwards? The tension. So if I wrote F equals MA, what am I going to put in for that? 60 newtons minus the tension equals 12 kilograms times, do we know the acceleration? 4 meters per second squared. And now I can do the math and rearrange this, couldn't I? What's the tension? It's going to be, take 60 minus that. What is it?
12.
Did you say 12? Hey, that's the same 12 as we got over here. What's that mean, kids?
Tension is equal.
The tension in the rope is the same everywhere, okay? So, I think we just did good with that, didn't we? All right, now, let's go try one of these guys. Who's ready for that? Isn't that what we did in lab last time? What if I had 2 kilograms hanging off and I had 8 kilograms in the cart? What does that pulley do? Any ideas?
No.
It just changes the direction of the force. Is it light enough to be considered massless?
Yeah.
We had those lightweight plastic pulleys, right? Frictionless. So could we say that we've got, let's draw all the forces. What are we going to put down here?
19.6.
Close. 1.96 newtons. How did you get that? How did you get the 1.96?
2 times 9.8.
Did I even know? I'm a liar. It's 2 kilograms, not 200 grams. 19.6 newtons. You were right. I apologize. I'm sorry. It's equal to mg, isn't it? Right?
I see how much you trust me.
I'm sorry. Lunch is on me, okay? So you got your 2 kilograms here. You multiply by 9.8. We're not saying that this thing's going to actually fall at 9.8 meters per second squared, are we? But if I cut the string, it would fall. So you know that the acceleration would be 9.8, and that now would give you the force of gravity pulling it down. Doesn't that force accelerate this whole system? So I don't have to worry about, there's a gravity pulling this down, but there's a normal force holding it up. I don't have to worry about that, do I? It's going to cancel out. So I don't have any force holding this thing back. All I'm going to do now is write F equals ma. What's the force pulling the system forward? 19.6 newtons equals what mass? 10 kilograms times A. What's the A? Does everybody get that? Can we find the tension in the rope? That's an internal force. I'm going to have to isolate one of the bodies. What if I isolated that body? I'm going to write F equals ma. What am I putting in for F? What am I putting in for M? 8. What am I putting in for A? 1.96 meters per second squared. And what do we get? 15.7? Good enough for me. We're 15.7. Are you good? Yes.
Is tension basically how the other body affects another?
Yeah. Well, that's the force that connects the two. Right? So let's take a look at the force connecting this one. We have a tension going up, right? Now, I want you to look at this and tell me if this is reasonable. How big should the tension be? Should it be bigger or smaller than the 19.6?
Smaller.
How did you know? That thing's dropping, right? It's accelerating down, so that's got to be smaller than that. Let's see. If the 15.7 is put up there, that makes sense then, doesn't it? Yes? You can go do the calculation again, and you're going to get the same acceleration. Are we good on this? Okay, let's try a problem with some friction now. You ready? Here we go. We're going to do 4 kilograms. It's going to get pulled forward with, say, 30 newtons. But the acceleration is only going to be 1.5 meters per second squared. Here is a surface. I'm telling you there's friction in the problem. Does this make any sense? What do you think the acceleration should be? What if we wrote F equals ma? What would you put in for F? 30 newtons. What would you put in for m? 4 kilograms. Hey, what would you get for your acceleration if you did that?
7.5.
Well, wait a minute. We only have 1.5. What's the matter?
Friction.
Which way is it going?
Left.
It's got to go this way. We have a force of friction. Is it moving?
No. It's not. Yeah.
Well, wait a minute. There's an acceleration. So it's got to have kinetic friction. What are we going to do now for my 30? I'm going to write 30 what? Minus the force of friction kinetic. Do we know what the acceleration is in the problem? 1.5 meters per second squared. Would you now be able to calculate that force of friction kinetic? Can you do the math for me and quickly give me an answer? Is it 24?
Yes.
Yeah, 24. 24 newtons is the force of friction. Does Newton's second law take into account friction then? Yeah, it works. Any questions on this? What if I said, what's the coefficient of kinetic friction? Wouldn't you need to know the formula for the kinetic friction? Who remembers that formula?
Force of friction over,
I know what you mean. Yeah, go ahead, say it.
well, it's the force of friction over the
Normal force is the mu. So we're going to rewrite it like that. Does that look familiar? I'm reviewing friction. It was a long time ago. Do we want to write in the weight of the object? What is the weight of the object?
39.3.
39.2 newtons. Then what's the normal force? 39.2 newtons. Are you good?
Yes.
So what am I going to put in for the normal force?
39.2.
I don't know what the mu k is, but I know what the force of friction is now. It's 24 newtons. Could you calculate the mu k?
0.612.
What is it?
0.612.
Does everybody get this?
39.2 from.
Mg. M times g is the weight of the object. Do you remember that? Okay, good. Do I have any more questions? Now, we are going through this stuff kind of like a review style. Normally, we'd be going much slower and letting kids try to figure some of this out on their own. You have all those numbers? Because guess what I'm going to do? I'm going to ask you for the same problem. Was that 30 newtons? What if we had an initial velocity in this direction? Oh, I don't want to have wheels on here. No wheels. Wheels usually means that we have no friction. What do you think that's going to do to the problem if I make the velocity to the left? It's going to slow it down, right? Which way is the friction going now? Good. Then you need to put in another force. What do we call this when we draw the forces on an object? A free body diagram. So do you think that the force of friction is going to change now, aside from its direction? Would the magnitude change? No. It's the same weight, the same normal force, right? Same surfaces. What is the force of friction? Who's got it? It's from the last problem. I erased it. 24 newtons. Will we still have an acceleration of 1.5 now? No. Let's write down F equals ma. And what are you going to put down for your F?
-30.
Not negative 30.
30.
I'm going to keep the right positive. I've got 30 newtons plus 24 newtons now. There's no minus, right? They're both going in the same direction. What do we put in for m? Now you can calculate the acceleration.
Why wouldn't you consider?
If the initial velocity is to the left, the friction is to the right. That's going to help bring it to a stop now. Friction's helping. If you wanted to stop something, friction's going to help you. What do you get for an acceleration?